All right, so I want to go ahead and actually go through the multiple choice section. We did talk about it in class, but I just want to make sure that we're reviewing carefully and that we feel totally comfortable with each question. So question number one, the specific latent heat of vaporization of a substance is the quantity of energy required to. So first of all, if we're talking about latent heat of vaporization, we're actually evaporating something. And if you remember, we've got two equations that we deal with in IB physics for heat. Q equals m times L. That actually applies to problem number one. And then we have the other equation, Q equals mc delta T. And let's be clear, this is when we're heating something up, and this is when we're actually changing its phase. Question number one, we're talking about a phase change. And whenever there's a phase change, there is never a change in temperature. Okay? Next, it's heat of vaporization. So the assumption here is that we're dealing with a liquid. Solid to vapor conversions, those can actually happen. That's what happens with dry ice, but that's not what we're talking about here. And lastly, D, I don't know what that is. They just got super specific, I guess hoping to mislead a student into circling that because it's overly specific. The answer is B, and in fact, that is exactly what the latent heat of vaporization is. Incidentally, A is actually what this letter C is here. I do that badly. So A is actually what this letter C here is, and that actually stands for the specific heat capacity, in case you were wondering. So that's question number one. Let's take a look at question number two. So we have two different objects. They're in thermal contact with one another. The objects are at different temperatures. So let's be clear. When we say two different temperatures, let's be clear. That means we have a hot object and a cool object. I'll call the cool object C. I'll call the hot object H. Hot and cool. Meow. Okay, so the temperatures of the two objects determine, well, heat always flows from high temperature to low temperature. So we're actually going to have this heat energy, this Q, this thermal energy. It's another term for heat. Okay, so these two objects are in thermal contact, which means they can actually exchange heat energy. The easiest way is that they're touching. So this is, in fact, choice C for number two. Nothing else really makes sense. Now, for number three. One thing we need to clear up, I actually gave this to everybody before break, but I pointed out that there is a quantity called electrical power that we're going to get to in January. Electrical power. And what it tells us is power equals the current times the voltage. Now, those are terms you haven't heard before, just I and V respectively. And so this is the formula we need for electrical power. Regardless of what the formula is, let's talk about what it can do. So when we're doing a problem like this where heat is not being exchanged, it's simply being dumped into a system. The formula we always want to use is Q equals mc delta T. Now, let's be clear. The energy in this case is the electrical energy that's getting converted into heat. And how do we go from power to energy? Power equals energy over time. So what that means is that our power times our time equals our energy. Now, they use the letter theta for temperature, so I'm just going to change that here to theta. So what does this tell us? The energy gained is the power times the time, and that equals m times c times this quantity delta theta. Now, the quantity they want us to isolate is, in fact, the specific heat capacity. When we go ahead and do that, we're going to get that the specific heat capacity is power times time divided by m delta theta. But power is current times time, that I times V times T, all over m delta theta. And that's how I'm arriving at choice A for my answer to number 3. So that's page 1 of the practice exam.